Today we're going to talk about predicting products of chemical reactions, and we're going to focus today on the first three types of reactions that we discussed earlier: addition, decomposition, and combustion reactions. Now for addition reactions are easy to point out and easy to pick out whenever you're looking at them and trying to predict products, because you'll end up with two elements, and that's always what I want you to write down first, just to label whether they're elements or compounds, because that's going to help us decide what type of reaction it is. I'm going to give you the simpler addition reactions, so there are always going to be two elements involved in this particular type of reaction. Now, some things to remember: make sure you watch for diatomic elements. Make sure you find charges on elements in ionic compounds, and don't carry over subscripts. Do not carry over subscripts. Now, I've honestly found that it's often easier if we write it in words first, when it's like this one is a formula equation. So calcium plus oxygen. Now notice I'm doing this in green, so that means you don't have to do it this way. It just can help. So if we put calcium and oxygen together to form a compound, we're going to get calcium oxide. Remember, we always put the positive one first, the negative one second. Since calcium is a +2 for a common ion charge and oxygen is a -2, that puts calcium first. Besides, think about it, would oxygen calcide even sound right to you now? It would not. So make sure you write it this way. So when we rewrite this then as a formula equation, I do want you to rewrite it. We're going to have calcium plus our oxygen. Calcium oxide, we've already established that calcium is a +2 and oxygen's a -2. One thing I ask people to do sometimes on this is to simply write the elements together in the compound. You could call it a skeleton compound if you want to. Remember, don't carry over those subscripts. Oxygen's diatomic when it's an element, but not when it's in a compound. Since we've already established that this is a +2 and a -2 charge, we don't need any subscripts for calcium oxide. It's good as it stands. Now, the last thing that you need to do after you write the product of the reaction is to balance it. So after you've gotten the products, go ahead and put those dashes in front. So now all we can put down are coefficients. We can't put any more subscripts in. Looks like since there's two oxygens on the left but only one on the right, we're going to need a 2 in front of the calcium oxide, giving us our 2 oxygens on both sides. But in the process of doing that, we unbalance calcium, so we'll need a 2 in front of calcium as well. So this is the final equation that I want, the clean equation. Make sure you don't have any charges in there. Just want just the answer in there. Okay, so the next one is already in words. I kind of wish I had written this differently. I wish I'd put chlorine plus potassium instead of potassium plus chlorine. I didn't, but I do want you to keep in mind that you're not going to just automatically put them in the order you see them on the paper. You have to pay attention to what their charge is. Since these are both elements, we know that this is an addition reaction. Of course, it's under the addition column or the addition heading in our notes, but that's how you would tell if it were on the worksheet. So we've got two elements. We know that's going to form a compound, and potassium chloride is a compound it's going to form. And if this were written in the opposite way and you wrote down chlorine potasside, I would hope that just saying that name would sound completely wrong. So now we're going to write the skeleton equation first of all. Potassium plus chlorine. Now remember, if it's an element, we have to check to see if it's diatomic, and chlorine is one of our hydrogen 7, our diatomic elements, and that's going to form potassium chloride. Remember, potassium's a +1. Look it up on your periodic table. Chlorine's a -1, so we don't need any subscripts. It's just going to be KCl. So now we've predicted the products of this. We've got the skeleton equation. So the very last thing we do is to balance it. Put those dashes in front. Looks like we need a 2 in front of KCl in order to balance our chlorines, 2 on each side, and that unbalanced our potassiums, so we'll need a 2 on the other side as well. So that, if you're still having trouble with balancing equations, you need to either come see me or you need to watch and go through that video again to make sure you know what you're doing. Okay, let's move on to decomposition. Decomposition reactions are easy to pick out as well, because decomposition reactions are going to start with only a compound. That's it, just a compound. We're supposed to watch for diatomic elements again, and again, do not carry over subscripts. The only way you're going to ever carry over subscripts is if they're part of a polyatomic ion, and that's not going to happen in our addition and our decomposition reactions. So you may want to go ahead and write out, and I should have written that in green. I'm going to correct that really quickly. Not well, it's kind of sodium iodide. And since all we're starting out with is a compound, that's going to break up into its elements, sodium plus iodine when it's the element, change it back to its original ending. And now we're going to write our skeleton equation. Make sure you rewrite. At this point, I'm not going to make you do anything with the types of chemicals they are. As far as solid, liquid, gas, you can leave those off in the final reaction. I want us concentrating on formulas right now. So the sodium iodide is going to react. It's going to decompose. We're going to get sodium and iodine out of it. Now, make sure you remember that iodine is diatomic, so it's going to need a 2 when it's an element by itself. So make sure you remember to check for the hydrogen 7, check for those diatomic elements. So now we balance. Looks like we need a 2 in front of sodium iodide to balance our iodines, and now we'll need a 2 in front of sodium to balance sodiums on both sides as well. So there's our decomposition reaction. Our next example of a decomposition reaction says solid iron 3 sulfide is decomposed by heat into its elements. So we've got iron 3 sulfide, Fe with sulfur. Remember, that does not mean it's Fe3S. I don't know how many times I get Fe3S as the chemical formula for this. That 3 does not stand for how many irons are in this compound. It stands for the fact that iron is a +3. And since sulfur, if you look it up on your periodic table, is a common charge -2 for its ion, remember what we can do with a 2-3 or 3-4 combination, we can cross those. So that means the 2 is going to go with the iron, the 3 with the sulfur. It's going to decompose into its elements. So we're going to end up with iron and sulfur as the 2 elements. Neither one of those are part of the hydrogen 7. Neither one of those are diatomic, so we do not put any 2's after them. Now all we simply have to do is to balance. Remember, never find a charge on an element. Charges do not belong on elements. They're only used in compounds to determine subscripts, so don't fall into that trap. So it looks like we need 2 irons and 3 sulfurs to balance this. So those are our addition and decomposition reactions. Let's look at our final one, our combustion reactions. Combustion reactions are really the easiest ones. The biggest problem people have is forgetting to include oxygen. It says hexane undergoes complete combustion, and it very nicely gives us the formula for hexane. But people are always going in and putting the arrow. We know that the same products for complete combustion for the fuels I'm going to give you this year are always going to be the same for those carbon, hydrogen, possibly oxygen compounds. It's always going to be CO2 and H2O. Now, hopefully you'd realize when you start balancing this that something's wrong because there's no oxygen anywhere. And that's because there's no oxygen here. You've got to have that oxygen in a combustion reaction. So let's balance this. Looks like we start out with 6 carbons on both sides and 7 water, or 7 hydrogens, or 7 waters on the right-hand side, which will give us 14 hydrogens on each side. So when we start to look at our oxygens now, remember we add up all of our oxygens. We've got 12 oxygens here, and we've got 7 oxygens here for a total of 19. Guess I don't need those parentheses in that position, for a total of 19 oxygens. Remember, if we have odd oxygens, we're never going to be able to get it to balance. When that happens, we're going to need to make sure and go back in and double everything except oxygens. So we're going to double our C6H14. We're going to change our carbon dioxide, double it to 12. We're going to double our water, change it from 7 to 14. Double the values that are below as well. When we double this, we end up with 24 oxygens here. We end up with 14 oxygens here. We end up with 38 oxygens here. Double everything except our final oxygen blank on the left. Looks like to get the correct number of oxygens, 38 divided by 2, I need 19 oxygens on the left-hand side in order to balance my oxygens. So 19 diatomic oxygens for a total of 38. So that's, and of course on your paper, please make sure you don't just cross out your 6 and your 7 over the right. Make sure you erase those and put in the 12 and the 14. Don't want a sloppy paper. Okay, our last one for incomplete combustion. Remember, the only thing that's different in incomplete combustion is one of the products. We've got C4H10 plus O2. Incomplete combustion, remember, we get carbon monoxide and water. When we have incomplete combustion, that's the only difference. So now let's go ahead and balance. Looks like we need 4 carbons here. And looks like since we have 10 hydrogens on the left, if we put a 5 in front of the water, we'll have 10 hydrogens on this side. So now we start looking at our, adding up our oxygens. We've got 4 oxygens here, 5 oxygens here, and that gives us a total of 9 oxygens. So what are we going to have to do in this case? Yes, we're going to have to double everything except the oxygen on the left-hand side. So we'll double the C4H10. We'll change this 4 to an 8. We will double our waters, change that to a 10. I'm going to write in our plus again since it got kind of covered up. Then make sure you double everything else too. We end up with 8 here, 10 here, 18 here. So now that we've doubled everything except the oxygen on our left-hand side, now we can go back and say, okay, 18 divided by 2 is 9. So if I put a 9 in front of this oxygen over here, we'll end up with our 18 oxygens on both sides.